Hello everyone, welcome back. Selman here, Physics 150 discussions on YouTube. So we have problem 8 from chapter 11 here, and let me read that out. So we have a figure which I've redrawn in which you have a long wire, not necessarily long, but of length L that's being suspended by wires that we're assuming are massless, and you've got a battery there just to show you that there could be a current that is running through this circuit, and it's being suspended vertically so that it's being hung down from a ceiling perhaps, and there is a magnetic field that is going into the page, and you can see that. We know the length of the wire is 50 centimeters and the mass of the wire is 10 grams. We also know the magnitude of the B field that's going into the page. Now, we set up a coordinate system so that the wire with length L is running across the x-axis. We see that the vertical direction is Z, and that the B field going into the page is going to be proportional to the y direction. So what we want to do is, what are the magnitude and direction of the current in the wire needed to remove the tension in the two supporting wires? So let's just think about what's going on here. We've got a couple of different forces at play. There's the gravitational force, which is vertically downwards. And there is some tension in these wires, which is helping to suspend the wire of mass M. So there's some tension T, like so. And the question is, what is the magnitude and direction of the current in the wire needed to remove the tension in those two supporting wires? So there's a third force, which you might have guessed, and this is the magnetic field force. And essentially, we're going to see that we're going to want it to be in the vertical direction as well, so as to reduce the tension all the way to 0. So let's sort of scroll down a little and write this out more mathematically. What we know is that the wire is in equilibrium. So what that means is that the sum of the forces, the gravitational plus the magnetic plus the tension, have to all equal to 0 newtons. What we also know is that we are setting the tension to be equal to 0. We want to find what the magnitude of we want to find what's happening to the current in the wire when the tension is equal to 0 newtons. So those two facts imply that we have the gravitational force plus the magnetic force are equal to 0 newtons. Or equivalently, what we can say is that those two things are equal and opposite. Equal in magnitude, opposite in direction. Okay, we still have a little bit more juice that we can squeeze out. We see, for example, that the gravitational force, and we know that it is vertically downward, so we can actually write that more explicitly. In fact, we know that we can write the gravitational, so I don't want to write this different each time. So we're using capital G. This, we know, is going to be minus the mass of the wire times the acceleration due to gravity in the Z direction, or as we like to say, the K direction. And so what that ends up meaning is that the magnetic force has to equal negative that, which means it's got to be equal to positive mg in the K direction. not altogether surprising that in order for the magnetic force to help suspend the wire, then it needs to counteract gravity so that it is going vertically upward. We also know that there's a B field that is running through, that there's a B field going into the page. And so there's also this battery. So we know that there's going to be some sort of current flowing. And the question is, what does the current need to be? What direction does the current in the wire need to flow in order for this magnetic force to be upwards like that? So we know that the B field is into the page. So let's actually write that down explicitly, what that means. So note the B field is into the page so that it's some magnitude, the 0.5 Tesla, in the J direction. And when there's a current flowing through the wire, what that means is that there's going to be a magnetic force, which is given. The magnetic force on a current carrying wire is given by the magnitude of that current times L crossed with B. Now, you can actually do a little bit of massaging with this, because you can also write this as L times I crossed with B. And for our, just because of the way that the problem is phrased, it makes more sense to write it like this. And the reason you can do this is because the current is, of course, flowing in the direction of the wire. So whether you put the directionality on the wire, the length of the wire, or the current, doesn't much matter. Those need to be going in the same direction. So you can write it as I times L vector or L times I vector, and that doesn't much matter. You can sort of play with that as much as you want. Actually, if you look at the derivation in the book, you'll see that pretty manifest. So we're going to assume a direction for this. We see that the wire is in the X, lying along the X-axis. So let's just give some value for the current that's in the X direction. So it's going to be, it could be going to the left or to the right. We're going to leave that sort of arbitrary in the following sense. So let's write down the I vector. It's going to be some I value, which could be positive or negative. That's what we want to solve for. And it's going to be in the X direction. So I times I hat. And I can be positive or it can be negative. So when we solve for that, when we plug everything in and make everything work out, we'll see whether we should have chose a positive or negative. We're going to later confirm just by sort of the right-hand rule that this is the way that made sense. So putting everything together, we have that the magnetic force is going to be equal to the length, which we know, I crossed with B. So this is L times the vector I is I. This is the quantity we want to find, times I hat, crossed with B, which we know in the J direction. Now I can take out all those constants, L, I, B, and this is I cross J. Quick examination with the right-hand rule shows that this is going to be equal to K hat. So that the magnetic force is going to be equal to I, L, B in the K direction. And we want this to be equal an opposite to the gravitational force. So what you have is the fact that ILB K hat is equal to mg K hat. Now this is only equal if the constants next to the K hat are equal, so I can just sort of get rid of that. And so I have ILB is equal to mg. Now there's nothing here on the right hand side that's negative. The mass and the gravitational constant, these are just numbers that are positive. Remember, the negative of the gravitational force was already accounted for in the direction. So the right hand side is positive, therefore the left hand side must also be positive. But L and B are also positive, therefore we see that this is also going to be a positive number. And now we want to actually solve for the magnitude of that positive number. So we're going to divide by the length times the magnetic field. You get that I is equal to mg over LB. So if I want to write the vector itself, this is I is equal to mg over LB in the I direction. And since we have each of these numbers at hand, we can actually figure out what this is, put in what the mass is, put in what the gravitational constant is, so on and so forth. You can show that this is 0.39 amps in the positive x direction, going from left to right, as Jesse's solutions say. And just so that's exactly what one might expect if you just sort of look. I mean, this is, if you just look at the picture and you take your, so imagine, I can't show you doing this because it's on my screen, but if you do the right hand rule and you take your thumb in the direction of the wire going to the right and the B field going into the page, you'll see that your third finger is going to be pointing vertically upwards. And so that's how you could have sort of surmised that the magnetic force should be going upwards as well. But you can also just do it out. So this is an interesting little problem, and I hope that this was helpful. If you have any further questions, by all means, leave a comment or send me an email. Okay, so I hope that was useful. Bye.